For decades, Mars has been the focal point of humanity's space exploration efforts. We've explored its surface with rovers, mapped its landscape from orbit, and even planned for crewed missions to its rocky terrain. However, Mars is only the beginning. The real adventure lies beyond, toward the outer planets and the farthest reaches of our solar system. Beyond Mars are gas giants with their many moons, icy bodies in the Kuiper Belt, and the boundary of the solar system itself, the Oort cloud. These distant regions hold clues to the formation of our solar system, the potential for extraterrestrial life, and even the future of human colonization. The journey beyond Mars is filled with challenges, but the possibilities are tantalizing. What could we discover out there? And how will we rise to the challenge of exploring these far-flung worlds? Jupiter is more than just a planet. It's a complex system with its own gravitational dominance. As the largest planet in our solar system, Jupiter's massive size and powerful magnetic field have shaped the orbits of many objects, from comets to asteroids. Its gravitational force is so strong that it has been called the protector of our solar system, as it can deflect potentially dangerous objects away from Earth. Its influence extends far beyond its immediate surroundings, making it a major player in the dynamics of our solar system. With dozens of moons and fascinating phenomena in its atmosphere, such as the Great Red Spot, a centuries-old storm larger than Earth, Jupiter is a rich target for scientific study. One of Jupiter's most exciting moons is Europa, which holds the potential to answer one of humanity's biggest questions. Are we alone in the universe? Europa is one of the most exciting places in the solar system in the search for life. Beneath its icy shell lies a deep ocean that may be warmed by tidal forces from Jupiter's immense gravity. Scientists speculate that hydrothermal vents on Europa's ocean floor could provide the necessary conditions for microbial life to thrive, much like similar ecosystems in Earth's deep oceans. These vents, rich in minerals and heated by the moon's internal energy, could support a variety of life forms, even in total darkness. The NASA Europa Clipper mission, scheduled for the 2020s, aims to fly by Europa and analyze its ice and subsurface oceans to understand its potential for habitability. If life exists in Europa's dark, icy depths, it would be one of the most significant discoveries in the history of science, changing our understanding of biology and our place in the universe. Europa's ice-covered surface, crisscrossed with cracks and ridges, holds tantalizing clues about its geologic activity and the liquid water that lies beneath. The surface appears relatively young, suggesting ongoing geological processes, possibly driven by its internal ocean. This could mean that Europa's ocean is actively interacting with the surface, a key factor in determining its habitability. Missions to Europa aim to penetrate its ice to explore these possibilities further. Proposals for future missions even consider landing probes on the surface or sending robotic submarines into its hidden oceans. The vast potential of this ocean world may unlock answers to questions humanity has asked for centuries. Is life possible elsewhere in our solar system? Could Europa's ocean harbor microbial life? Or something even more complex? The discoveries waiting beneath Europa's icy shell could reshape our understanding of life's resilience and the environments in which it can exist. Now, let's talk about some of the most fascinating moons in our solar system. These moons are more than just natural satellites. They hold clues to the potential for life beyond Earth and the future of human exploration. First, let's dive into Ganymede, the largest moon in the solar system. Ganymede is even bigger than the planet Mercury, and its size isn't its only standout feature. It's the only moon known to have its own magnetic field. This magnetic field suggests that Ganymede has a complex interior, possibly with a liquid iron core, something typically seen in planets. Scientists also believe that Ganymede has an ocean beneath its icy surface. This subsurface ocean, which might be sandwiched between layers of ice, could hold more water than all of Earth's oceans combined. And where there's water, there's the potential for life. The presence of this magnetic field could also protect the moon from harmful radiation, making it a safer target for future exploration or even colonization. Ganymede's unique characteristics make it one of the most exciting destinations in the search for extraterrestrial life and a possible future home for humans. Next, we turn to Callisto, the second largest moon of Jupiter. Callisto stands out because of its ancient and heavily cratered surface, which appears untouched by volcanic or tectonic activity for billions of years. This moon is essentially a time capsule, providing a glimpse into the early solar system. Callisto's distance from Jupiter's intense radiation belts makes it an attractive location for human exploration. With its abundant water ice, Callisto could be a critical resource hub. Water from the ice could be used for drinking, generating oxygen, and even converting into rocket fuel, making it a key outpost for deeper space missions. Imagine a future where a base on Callisto serves as a gateway for human missions to the outer planets and beyond. Its ancient surface might not have the dynamic activity of moons like Europa or Io, but it holds immense potential for human exploration. Now, let's shift our focus to Saturn and its iconic rings. Saturn is known for its majestic ring system, but the true wonders of the planet lie in its moons, especially Titan and Enceladus. Titan, Saturn's largest moon, is unique in our solar system because it has a thick atmosphere. In fact, Titan's atmosphere is thicker than Earth's. This nitrogen-rich atmosphere, combined with clouds of methane and ethane, gives Titan its signature orange haze. Beneath this thick haze is a landscape that resembles early Earth, with rivers, lakes, and seas, not of water, but of liquid methane and ethane. Scientists are particularly excited about Titan because it is the only place in the solar system other than Earth known to have stable bodies of liquid on its surface. These methane lakes could harbor life, though it would be vastly different from life as we know it. Titan's atmosphere and low gravity also make it an ideal location for flying exploration vehicles. In the 2030s, NASA's Dragonfly mission will send a rotorcraft to explore Titan's surface and atmosphere. This mission will be groundbreaking, as it will allow us to study Titan up close and search for signs of life in its lakes and seas. Finally, let's talk about Enceladus, a small moon that packs a big surprise. Enceladus gained attention when NASA's Cassini spacecraft discovered plumes of water vapor and organic molecules erupting from its surface. These plumes indicate that Enceladus has a global ocean beneath its icy shell, heated by hydrothermal activity on the seafloor. The combination of water, heat, and organic molecules makes Enceladus one of the most promising places in the solar system to search for life. Scientists believe that these hydrothermal vents could host microbial life, similar to the ecosystems found around Earth's deep-sea vents. The plumes also make it relatively easy to sample the moon's ocean without having to drill through thick ice, making Enceladus an exciting target for future missions aimed at searching for signs of life. Now that we've explored Jupiter and Saturn's moons, let's move even farther out to the ice giants Uranus and Neptune and the vast reaches of the Kuiper Belt. While Jupiter and Saturn have been explored extensively, Uranus and Neptune remain largely mysterious. These ice giants, composed primarily of water, ammonia, and methane, represent a less explored region of our solar system. Missions to these distant planets are rare due to the immense distances involved, but the scientific rewards could be extraordinary. Let's start with Uranus. Uranus is a strange world with an extreme axial tilt, 98 degrees relative to its orbit. This unique tilt means that each of its poles experiences 42 years of sunlight followed by 42 years of darkness, creating bizarre seasonal changes. Scientists believe that this tilt was caused by a massive collision early in Uranus history, possibly with a large protoplanet. This unusual tilt also affects Uranus's magnetic field, which is tilted at a different angle from its rotational axis, creating a lopsided magnetic bubble around the planet. Studying this magnetic field in greater detail could help us understand more about Uranus' internal structure and history. Uranus also has 27 moons, with Miranda, Ariel, and Titania being the most interesting in terms of geological activity. These moons feature vast canyons, icy cliffs, and evidence of tectonic shifts, landscapes far more dynamic than initially expected. Miranda, for example, has cliffs that are 12 times higher than the Grand Canyon, Future missions to Uranus could explore these moons, potentially revealing more about their formation and evolution. Voyager 2 remains the only spacecraft to have flown by Uranus in 1986, leaving us with many unanswered questions. A dedicated mission to Uranus would allow us to study its mysterious atmosphere, magnetic field, and unusual moons up close. Next, let's move on to Neptune, the furthest planet from the Sun and a world of striking blue storms. Neptune's atmosphere experiences some of the most extreme weather in the solar system. Its winds can reach speeds of over 1,200 miles per hour, faster than the speed of sound. The most well-known storm is the Great Dark Spot, a massive hurricane-like storm that appears and disappears over time. Neptune's atmosphere is composed mostly of hydrogen, helium, and methane, giving the planet its brilliant blue color. Studying these storms could help us understand how weather systems work not only on other planets, but also on Earth. One of Neptune's most fascinating features is its largest moon, Triton. Triton is a unique moon for several reasons. It orbits Neptune in the opposite direction to the planet's rotation, a phenomenon known as a retrograde orbit. This unusual orbit suggests that Triton may have originated in the Kuiper Belt and was later captured by Neptune's gravity. Triton also has geysers that eject nitrogen gas, hinting at active geological processes beneath its icy surface. Triton might even have a subsurface ocean, similar to other icy moons like Europa and Enceladus, making it a prime target for future exploration. Triton's retrograde orbit and potential ocean make it one of the most intriguing objects in the solar system. Now, let's go even further out to the Kuiper Belt, a vast region of icy bodies that includes Pluto and other dwarf planets. These objects are remnants from the early solar system, offering valuable clues about its formation and evolution. The New Horizons mission, which flew past Pluto in 2015, revealed that Pluto is far more dynamic than anyone expected. Pluto's surface is covered in towering mountains of water ice, flowing glaciers of nitrogen ice, and a thin atmosphere that expands and contracts as it orbits the Sun. More surprising was the discovery of potential cryovolcanoes and a subsurface ocean beneath Pluto's icy surface, raising the possibility that it could harbor life, though in forms vastly different from those on Earth. The Kuiper Belt is home to other interesting objects such as Eris, Haumea, and Makemake, dwarf planets that may share some characteristics with Pluto. Exploring these distant worlds could help us better understand the early days of our solar system and how planetary systems form and evolve. The outer solar system holds some of the greatest mysteries, and missions to Uranus, Neptune, and the Kuiper Belt could provide critical insights into the nature of these icy worlds. Exploring the outer solar system is a thrilling challenge that pushes the boundaries of current technology. Vast distances, harsh environments, and long mission durations present major hurdles that make exploration difficult. One of the biggest challenges is the sheer distance to the outer planets. Reaching Jupiter, Saturn, Uranus, or Neptune can take years. NASA's New Horizons mission, which flew by Pluto in 2015, took 9 years to reach its destination. A mission to Uranus or Neptune could take 12 to 15 years, while missions to the Kuiper Belt or Oort cloud would take even longer. These long travel times mean spacecraft need to function autonomously for extended periods. They require reliable systems capable of operating without regular updates or repairs from Earth. Power, communication, and scientific instruments must all work effectively throughout the mission's journey. Another challenge is cosmic radiation. Beyond Mars, the protective bubble of the heliosphere weakens, leaving spacecraft exposed to higher levels of cosmic rays and solar radiation. For example, Jupiter's radiation belts are particularly intense, posing a serious threat to spacecraft electronics. Missions to Jupiter's moons, like Europa, need advanced shielding to withstand this radiation. For human missions, the radiation challenge becomes even more critical. Astronauts face long-term health risks from cosmic rays, and current technology may not yet be sufficient to offer full protection. In addition to radiation, extreme cold is another obstacle. The outer planets are far from the Sun, leading to incredibly cold conditions. Temperatures can drop as low as -200 degrees Celsius. Spacecraft must be designed to operate in these frigid environments. Since solar panels are ineffective at these distances, outer solar system missions rely on radioisotope thermoelectric generators, RTGs, for power. RTGs convert heat from radioactive decay into electricity to power the spacecraft. Although RTGs are reliable, they have a limited lifespan, so missions need to carefully manage their energy usage over long periods. Communication delays are another factor. As spacecraft travel farther from Earth, the time it takes for signals to reach them increases significantly. For example, a signal to Pluto takes over 5 hours. This makes real-time control impossible for distant missions, so spacecraft must operate autonomously, making decisions without waiting for input from Earth. This requires sophisticated systems to handle malfunctions or adapt to unexpected conditions. Despite these challenges, space agencies are developing innovative technologies to overcome them. Improved propulsion systems, more efficient power sources, and enhanced radiation shielding are bringing us closer to exploring these distant worlds. Exploring the outer solar system is not easy, but it's essential for expanding our understanding of the universe. The discoveries we make will not only deepen our knowledge of the cosmos, but may also bring us closer to sending humans to these distant planets one day. Thanks for watching. Follow us for more updates on space exploration.